right, with the logistics out of the way, let's get into the introduction to operating systems. So we use computers and we run various programs. The programs could be a web browser, uh, could be PowerPoint, uh, Kakao Talk, you know, many different things. Now, these programs, they're executing by basically by following instructions, right? So first, the processor within the computer would fetch an instruction from memory. Now, after that, it also needs to actually figure out what that instruction is. So there's a decoding process, and then after decoding, it actually goes on to execute. So the execution could be as simple as adding two numbers, accessing memory, checking a condition, jumping to a function, and so forth. And then the processor moves on to the next instructions and so forth, right? So that's really what happens when we're running a program in a computer. So what's an operating system here, right? So OS is responsible for making it easy to run programs, and allows various programs to share memory and also enable programs to interact with devices. So basically, OS is in charge of making sure the system operates correctly and also efficiently. So throughout the semester and in the textbook we're using, there are actually three main concepts. The first one is virtualization. And if you took 209, we talked about this, right? Because this is one of the most beautiful concepts in systems. So what the operating system does, it takes a physical resource, like CPU, for instance, and transforms it into a virtual form of itself. So physical resource could be a processor, memory, or disk, and the virtual form is a more general, powerful, and easy to use. And we'll talk a little bit more about what we mean by that. And sometimes, thus, we refer operating system as a virtual machine. So again, if you think back about 209, we did learn a lot about a bunch of different system calls. And this system call is what allows us, the users, to tell OS what to do. And the operating system kindly provides some interface that we can use to do this. For instance, APIs and standard libraries. A typical operating system would export a few hundred system calls. It runs program, accesses memories, and devices. So one might argue a very quick definition of operating system is OS is a resource manager, right? There are resources in a computer. It assigns, deassigns, schedules, basically managing those resources. And the resource includes CPUs or even GPUs these days, memory, and disk. So what the operating system does is that there are many programs within a computer that we run, right? So if you're using Windows, for instance, you can actually show a list of processes, programs, same with Mac and Linux, etc., right? So many programs to run, but there could be just one CPU, right? So they need to share, right? And with virtualization, they actually think they have entire access to the CPU, right? Also, many programs to concurrently access their own instructions and data. So this could be done by sharing memory, and many programs to access devices like sharing disk. So let's first look at CPU virtualization. All right, so system has a very large number of virtual CPUs. This is virtual, so you can get as many as you want. So you were really converting a single CPU into a seemingly infinite number of CPUs, where each process thinks it has full access to the CPU, like creating that illusion, right? It also allows many programs to seemingly run at once. So this is virtualizing the CPU. So let's use a simple example. And this is a code that loops and prints. Now, I'm not going to go line by line on the code, because first of all, you already should know when you look at the code what this does, right? So if you can't, I don't think you'll be able to survive this course. So anyways, so simple code, right? So if you go through it, basically, you get some inputs, you look at the argument count. When the user uses it correctly, basically what it does is, it has this infinite loop as while one, then you spin, which is repeatedly checking the time and returns once it has run for a second, right? Then it prints. That's it. Now, this code was called CPU.c, and we'll run GCC to compile it. And once you execute, right, it's just going to keep printing this, every second. Just go on and on and on until you press Control-C. Okay? Now, the same code. Let's say on the prompt we do .cpu A, and you run it on the background, right? And we're running 4 different instances of this, right? So we have 4 different processes. And since we have A, B, C, D, it will just keep printing it, right? Now, remember, we just have one processor, but these 4 programs seem to be running at the same time, right? This is what OS does by virtualizing the CPU. Let's look at how to virtualize memory. Now, the actual physical memory is really an array of bytes, right? And a program will keep all of its data structures in memory. It would read, basically load, and it specifies an address to be able to access the data. When you write, you're actually storing, right? You specify the data to be written to the given address, right? So you read from an address and you write to a certain address. Again, a simple code. This is a code that simply accesses memory, right? So initially you allocate some memory, right? And then you're printing out the address of the memory, right? And then you put 0 into the first slot of the memory. And then again, you put it in the loop and you're incrementing by 1 and then print. So that's the 4th. So if you do a program output, and again, this was code mem.c. So initially, it was allocated in the memory at address here. And then you just keep running, right? You increment by 1. P's 1, 2, 3, 4, 5. So updates the value and prints it out until, again, you do Control-C. Now, if you run it multiple times, right? Here, again, you're running it twice. So you have 2 programs, right? They're both assigned same address, right? Now here, this is as if each program has its own private memory, right? So each running program has allocated memory at the same address, right? So you have to remember this is not a real physical address, right? This is a private address of that program. And each seems to be updating value independently at that address. So this is virtualizing memory, meaning each process accesses its own private virtual address space, right? This is by virtue of operating system. So obviously the operating system needs to be able to convert these virtual private address into a real physical address, right? So OS maps the address space onto the physical memory. Excuse me. So a memory reference within one running program does not affect the address space of other processors, right? It shouldn't. So physical memory is a shared resource that is managed by the operating system. Now, moving on. So the operating system would often face something called a concurrency problem. So because OS is juggling many things at once, right? You're first running one process, another, and so forth, right? So there's in the modern programs, they are multi-threaded, and they also exhibit the concurrency problem. Now, note that we talked about three key concepts. One was virtualization. Second is concurrency, right? So here we have a multi-threaded program. This is a little long, so it actually goes over. So here, I mean, if you don't understand threads and all that, actually it's okay. Because we're gonna deep dive into this, I think we believe in the second half of the semester. But right now, what we need to understand is the program creates two threads, right? Now, a thread is a function running within the same memory space, and each thread starts running in a routine called worker here, which is basically in a loop, you increase the counter, okay? Yes, worker simply increments the counter at the end. So before threading, it actually prints out the initial value of the counter and then at the final value. So here the loop, right, was number of times where each of the two workers will increment the shared counter, right? Remember, the counter was actually the same, right? Now, if we loop 1000, right? Remember, there are two threads, right? So this should be 1000 times 2, right? So initially 0. This is 1000 times 2. Now, if we had, let's say, 5 threads, this should be 5000, right? What's interesting, however, if you have a large number of loops, let's say 100,000, if you do this, you're going to have initial value of 0, but some weird final value. You run it again, also weird value, and also different value, right? So what the hell is going on, right? Now, incrementing a shared counter is actually following 3 instructions. Number 1, you're loading the value of the counter from the memory into the register, right? Then you increment it and you store it back to the memory. However, the key point here is that these 3 instructions, they're not being executed atomically, meaning they're not being executed all at once. So here the problem of concurrency happens. So we need to have some persistence because devices such as DRAM, they store values in a volatile, right? This is dynamic, it's not forever. So if it crashes, right, you might lose it. So there need to be some hardware and some software capabilities to help store data persistently. So in terms of hardware, there could be I/O devices such as a hard drive or even solid state drive, right? SSDs. A software, there's something called file system. So file system manages the disk and responsible for storing any file that user creates. So another simple code here, we're going to create a file here, /temp/file. and that will contain the string hello world, right? So this is a code to do it, but only thing you want to remember, not only, but key thing you need to remember here is open, okay, write, and close. So here, open, write, and close, and these are system calls. They are routed to the part of OS called the file system. And the file system handles these requests. So persistence is the third theme of this textbook, right? Virtualization, concurrency, and persistence. So what does OS do to write to a disk? Well, first it needs to figure out where on the disk this new data will reside, and then it will issue some IO requests to the underlying storage device. Now, the file system handles system crashes during write, right? And there are some techniques such as journaling or copy on write, and it will carefully do the ordering write to disk. Again, we'll go into details of this. Remember, this is all intro to the OS part, right? Basically giving you a very highlight view of what operating system should do, right? So if you don't understand the details, that's okay. But just try to figure out the high level concepts. So we touched on three key ideas, three key concepts of operating system. And operating systems have some design goals, right? Number one, build up abstraction, right? So make the system convenient and easy to use. So virtualization is one way to do this. Also, everybody's into performance, right? You want something that's really fast, right? Or high capability. So you want to minimize the overhead of the OS. And providing virtualization is cool, but it has to be without excessive overhead, right? You don't want to try to achieve something by creating a large amount of overhead that affects the performance. There needs to be protection between applications, meaning you want some isolation. So bad behavior of one should not harm others in the OS itself. If there is something bad, something nasty, it's isolated. High degree of reliability, right? So it should be able to run nonstop, right? If the computer is on, it should be able to run, right? It should be reliable. There are also other issues like energy efficiency. If it's a mobile operating system running on battery, energy efficiency, key value, obviously security. You don't want your OS to be hacked. Mobility, right? Mobility could involve like, access to networks or whatever. And also it could be some physical damage, whatnot. So mobility involves many different challenges. But we have separate courses on mobility, probably at the graduate level. But certain operating system also needs to handle that. And also, energy efficiency mobility, you also have space restraints. It has to be small, so it has to be lightweight, but also be secure. So those are some of the design goals that operating system has.